Next speaker will be Igor dos Santos Gomes from Brazil, and he will talk about suitable materials for small blades. Once again, thank you very much, David Wood. And are you there, Igor?
Everyone hear me?
You there? Good.
Yes. Yes.
Thank you. I see you very well now.
I'm going to share my presentation.
Yes.
Can you see my presentation?
Yes, we can. Thank you.
Well,
welcome.
Thank you. Hello, everyone. I am Igor Gomes. I am a PhD candidate at Universidade Federal do Pará, Amazon, Brazil. Today, I'm going to talk about sustainable material for small blades. Summarize the presentation and the topic is introduction, small hydrokinetic and wind turbine blades, sustainable reinforcement material for final considerations, and reference. Introduction. The blades are one of the main components of wind and hydrokinetic turbines, and are responsible for converting the kinetic energy of water or wind into mechanical power. Combinations of material properties which are difficult to obtain with conventional materials: low density, high directional mechanical strength, high modulus of elasticity, high capacity to absorb energy on impact, and high chemical and environmental resistance. Composites reinforced by carbon fiber, boron, glass, cleveland have been widely accepted for structural and non-structural uses, including turbine blades. For the manufacture of composite materials in the last decade, environment concerns are increasing the demand for replacing existing synthetic fibers with biodegradable, renewable, low-cost vegetable fibers. In comparison with the traditional reinforcements, plant fibers, also called lignocellulosic materials, have acceptable specific strength properties, low density, low abrasion multifunctionality, good thermal properties, improved energy recovery, and cause less skin and respiratory irritation. And talking about small hydrokinetic and wind turbine blades, the blades can be manufactured in many configurations using different types of materials. There is not only one possible to design these blades. As we can see here in this picture, we see, for example, two types of blades, a large blade and a small blade. When you see the large blades, they usually do not have a core. They have a spar structure, a sandwich structure, and the shells are bonded in the leading edge and the trailing edge. But when we have a core in a small blade, for example, the core fixes the shells and provides resistance to flap-wise bending, for example. And the core of this type of blades are made in, usually from EPS, PVC, PET, PUR, and a natural fur that is balsa wood. And when we have conventional material for manufacture, we have, for example, manufacture technique that is CNC machine for manufacture a solid blade using, for example, aluminum alloy. That is interesting for the application underwater because aluminum has a resistance to corrosion, but depends on the length of the blade. The manufacturer can be very expensive because aluminum alloys generally are very expensive, but there is a low-cost manufacturer using, for example, natural material, that is a timber, a Pinus radiata timber, also using a CNC machine manufacturing. This timber is usually low-cost, soft to manufacture, and generally have a long life fatigue. And to protection the timber underwater is use epoxy resin and e-glass fiber to coat the core of the blades. And then another possibility for manufacture the blades and the sustainable reinforcement materials are the vegetable fibers from Brazil. Here in Brazil, we have different types of fibers. For example, fibers from the best, where we can see it jute, mallow, and fibers from the leaf, for example, curauá, miriti, Pará da Costa, that are type of fibers that are abundant in our region. And another type of fiber of the leaf also is sisal. We have banana that are cultivated in the northeast of our country. And we have açaí, we have tururi, we also have the petioles of miriti. That is the potential material for use as a core of a blade.
Igor, may I interrupt a bit? The connection is not very good, and to make sure that we can see on the screen, is it all right that we unmute your... Take the camera off. Yeah, we'll take the camera off. Is that all right? To make sure that we can see the...
Yes.
Okay, we'll do that. You just continue.
Turn off.
Yeah, thank you. You just continue.
Can you hear me? Can you hear me?
Yes, we can hear you. Yes.
So we have here the petiole of miriti. The tree, the palm tree that petiole of miriti came from is this one. And here we have the leaf of this palm tree. And in this leaf, we have the segments, the leaflet, that is this part, the lamina, that is this part, the leaf sheath, that is this part, and the petiole, that is this part. The petiole of miriti is the core of the petiole. Well, when we in a table see the different properties of, for example, the leaf of the fiber of miriti and the petiole of miriti, in the middle of those properties, we see the density. That is the most important property in this case, because petiole of miriti have a low density. That is a property that has a great impact in the performance of a turbine, because it provides a low rotation of inertia. Well, when we compare petiole of miriti with balsa wood, that is a widely material used as a core in blades, we see that the density of the miriti has almost the same range of the density of balsa. As we can see here, the density of the miriti is around 0.06 grams per centimeter cubic. Well, it makes these materials a potential materials for using this type of application. Well, when we see in another table some properties of this material as reinforcement of composite, we see that the properties of the composite using fibers of miriti or petiole of miriti depends on the manufacturing technique, the type, the fiber type, the reinforcement orientation, and the fiber contents. Well, this is property obtained from coupon tests. Well, about the manufacture technique used to manufacture small turbine blades using sustainable materials, we have different types of manufacturing. Here, for example, to manufacture a blade using flex fiber and polyester resin, a blade manufacturer using a CNC machine. And another type of manufacturing is, for example, a timber, a pinus radiata timber, coated with epoxy resin and e-glass fibers. It's another manufacturer uses CNC machine, but there is another possibility for manufacturing this type of blade, this type of small turbine blades, that is the hand manufacturing. In this case, for example, a blade manufacturer using templates for the profiles of the blades for manufacturing the section. It can be together with each other bonds to manufacture a blade using a natural material that is Belian wood. And from these blades can be manufactured another ones coping this blade. For example, in techniques using circular saw dig or roto dig, for example. And manufacturers technique that use molds to manufacture blades, small blades in this case. This technique was used to manufacture a 1.07 meters blade made using polyurethane as a core, coated with vinyl ester and jute fiber fabric. That is a fiber cultivated in Amazonia region. Well, in this case, the shells of the blade was manufactured using the molds, and then the mold was closed, and inside the mold was put polyurethane to expand and make the core of the blade. And the manufacturer using ethyl of mercury to manufacture a 0.598 meters blade using ethyl of mercury as a core coated with polyester and glass fiber was a combination of different techniques of manufacture. A technique that uses a hand manufacture to manufacture at first the shells, and also a vacuum lamination to avoid the air bubbles that exist in a hand manufacture, that is almost impossible to avoid in a hand manufacture. So in this case, we manufacture the shells in the surface of the blades using e-glass fabric, and in the surface of the mold we put gel coat to confer a good surface finish, and polyester resin. And we put a tube, a spiral tube to distribute the vacuum pressure in the mold, and then the mold was put inside the vacuum bag to manufacture 2 shells, for example, at the same time. Well, to manufacture the core of the blade, we will use a petile of mercury in blocks. In these blocks, we manufacture using templates on the section of the blade, the transverse section of the blade. In this section was drilled in the centroid and bonded with each other into the spar using polyester resin. In this case, we use a spar manufacturer with polyester resin, petile of mercury, and carbon fiber. And at final, we apply the polyester resin on the inner surface of the shell to anchor the core of the blade, and then close the blade to cure the polyester resin. And this figure, we see the blade manufacturing. We see the blade manufacture. And after manufacture, after cure the resin, the irregularity in the leading edge, in the trailing edge, was carried out. Also in the roots, in the tip, was carried out using polyester putty and sanding. And we see here also a metallic insert with a drill to make possible to fix the blades in the rub of the turbine. As we see here, because we used just one layer of e-glass fiber, we almost see inside the blade, we see the core of the blade, but we could use, for example, another material or more layers to provide more resistance to this blade. For example, we can use a jute fabric, mellow fabric. We can use a midi-chip fabric, arrange the ends in one directional, two directional, or multi-axial configuration. And also, we can fabricate the core of the blades not only in the transverse arrangement of the section inside the blade. We also can manufacture in a longitudinal orientation or mixing transversion and longitudinal orientation. Here we see the blade after manufacture, and here we see the blade painted. And in this table, we see that using petil of midi as a core, the blade manufacturer has a low mass and a low density, and consequently a low rotational moment of inertia. That is the key element to the starting performance of a turbine. Well, final consideration. Whatever method you're using for manufacturing blades, considerable care is needed to reproduce the design foil profile, especially near the tip, where significant errors in the blade shape could have large impact on the power output. Synthetic fibers are currently used to make small hydrokinetic and wind turbine blades due to their excellent mechanical properties and a specific resistance. However, these fibers are far from being suitable for local manufacturing, make them economically unfeasible in applications that generate energy in a small scale. For this reason, we discuss here the potential of vegetable fibers from Brazil with their good mechanical property, low specific mass, low processing cost, and easy to work. And they are biodegradable, coming from renewable source, which makes them attractive for this type of application, especially using petil of midi as a core of turbine blades. Here are the reference, and here are the acknowledgements. That's it. Thank you, everyone.
Thank you very much, Igor. It was really interesting and good to see that there'll be alternative material for producing the blades in the future. Really interesting. Thank you. Are there any questions for Igor? Not for the time being, it seems. Otherwise, we will continue with the last